video, we're going to begin our discussion of rates of change. So change is one of the major things we focus on in our study of calculus. So specifically, calculus is the study of continuous change. So what we're talking about in terms of change is how our function values, in other words, our outputs for a function, how those values change as input values change. So in other words, as our x values are changing, what we're analyzing is how the associated y values are changing in relation to those input changes. Now when we talk about a rate of change, we have two types of change in that sense. So one type is what we call the average rate of change. So the average rate of change is going to be the amount of change over an interval. So if we look at an x value to another x value and then the associated y values associated with those x values, the average amount of change over that interval is one type of change that we can discuss. Now we can also talk about instantaneous rates of change. Instantaneous. Is that right? Long word, instantaneous. There we go. Instantaneous rates of change. We're just going to focus on average rates of change in this video, and then we'll extend what we're going to talk about in this video to encompass this idea of instantaneous change. In other words, change at a single point, single location. So the average rate of change of y, of our function values with respect to x, specifically as our x changes from specific value x1 to specific value x2, is defined in the following way. So it's change in y, which is going to be y2 minus y1. So those are going to be the y values associated with x1 and x2. And because it's a rate of change in y with respect to change in x, it's going to be divided by the associated change in x. So you probably look at this and this probably looks very familiar. This probably looks very much like the slope of a line. So if you have a linear equation, you have 2 points on that line, coordinates x1, y1, and x2, y2, this would be the formula you use to calculate slope. So what we're going to talk about here is going to be very, very closely related to this idea of slope. But now we have to keep in mind that we're not necessarily talking about a line. We're not necessarily talking about a linear function. This x1, y1, and x2, y2 could be points on any function. So we're talking about those points and how our associated values are changing with respect to any function. Now, if we want to use function notation, which is going to be preferable for us, another way to write this, as opposed to y2 and y1, we could write using function notation as f of x2 and f of x1. And this is going to be the preferable notation for us. So the change in our function values divided by the change in our input values associated with those function values. If we think of that as a rate, then that is going to be the average rate of change as we go from x1 to x2. Now what this represents from a geometric standpoint is the slope of the secant line, and we'll define what that is in just a moment. It is the slope of the secant line that would pass through the points x1, y1, and x2, y2 on this particular curve representing this function f of x. So let's draw a picture of what this would look like. So I've drawn just a generic functional curve. Okay, let me scoot that up. There we go. So this curve represents some function f of x. We don't know what it is, but we know it has to be something whose graph passes the vertical line test, therefore making it a function. So imagine taking 2 points on this particular function, x1, y1, and x2, y2. So let's label those. So we'll call this location x1 and x2 because they're along the x-axis. And so the associated y values would be y1, and then if we trace this over about right there, that'll be y2, again because those are along the y-axis. Now we also decided that we could use function notation instead of actually calling these y values. So this could also be written as f of x1 and f of x2. So when we're talking about a secant line that passes through these 2 points, the secant line is going to be the line that we draw, the unique line that we would draw, that cuts through the curve at these 2 points. So you may have heard the term tangent line. A line that is tangent to a curve is only going to intersect that curve at that one particular location. It's going to be parallel to the curve at that one particular location. A secant line, on the other hand, is actually going to pass through the curve in those 2 locations. And so if we want to answer the question, what is the average amount of change per unit as we travel along the curve from x1 to x2? What is the average amount of change in our function values per unit as we travel from x1 to x2? And at that point, it's just going to be the slope of that secant line. And so using our function notation, it's y2, or f of x2, minus y1, or f of x1, divided by the change in those associated x values. That's going to be our average rate of change. So again, the idea is how much are the y values changing versus the associated x values. And so when we find that rate of change, that is going to be the amount of change per unit as we travel from x1 to x2 along this particular curve, and then trace those associated function values. So let's do a couple of examples calculating this average rate of change. So suppose our function is defined as f of x is equal to x squared plus 1. We want to find the average rate of change under several different conditions. So number 1, as x changes from 1 to 3, and then as x changes from 1 to 2, and then also as x changes from 1 to 1.5. So our average rate of change as x changes from 1 to 3 is defined as f of 3 minus f of 1. Notice it's the further out x value minus the closer in x value, divided by 3 minus 1. So as part of determining this average rate of change, we do have to determine both of those function values. So you can either do that within the formula for average rate of change, or if it's easier for you, you can go out to the side and you can do those calculations separately. I'm going to go out to the side and do the calculations separately. So first thing I want to find is going to be f of 1. Now notice we're taking change with respect to 1 for all 3 of these examples. So f of 1 is going to be used in all 3 of these situations, and we only need to calculate it the one time. So f of 1 is defined as x squared plus 1 evaluated at an x value of 1. So 1 squared plus 1. 1 squared is going to be 1, so 1 plus 1 is going to be 2. Now we also need f of 3. So f of 3 is going to be 3 squared plus 1. Okay, 3 squared is going to be 9. 9 plus 1 is going to be 10. So these are going to be the values that we substitute into our average change formula. So f of 3 is 10. F of 1 is 2. So our numerator is going to be 10 minus 2. And then our denominator is 3 minus 1. So now it's just a matter of simplifying down. So our numerator simplifies to 8, our denominator simplifies to 2, and if we simplify that fraction fully, that simplifies down to 4. So 4 is going to be the average rate of change in our y values as we progress from x equals 1 to x equals 3. So if you think about the total amount of change as we go from f of 1, which is 2, to f of 3, which is 10. In other words, we travel from 1 to 2, and then from 2 to 3. Essentially, the idea here is we're taking the total amount of change, which takes us from 2 to 10, in other words, a change of 8 units, and we divide it up over how many units we've traveled. So if we travel from 1 to 3, we've traveled a total of 2 units. Our y values have changed by 8 units. So the total change of 8 units divided up over those 2 x units is going to be 4 units traveled per unit x. So that's the general idea there. We're taking the total amount of change in our function values and dividing it up across how many x values we've traveled in order to average out how much change we have per x value that we move. Okay, so what if we're traveling from 1 to 2? In other words, we're traveling a shorter distance along this curve. So the average change here is going to be defined as f of 2 minus f of 1 divided by 2 minus 1. So we'll need f of 2. We already have f of 1. So I'm going to go out to the side. Let's determine f of 2. Again, same function. So 2 squared plus 1. 2 squared is 4. 4 plus 1 is going to be 5. So f of 2 is going to be 5 minus f of 1, which is 2. And then we're dividing by 2 minus 1. So our numerator is going to be 3. Our denominator is going to be 1, which simplifies down to 3. Okay, so what does the average rate of change mean here? Well, if we go from 1 to 2, those are x values, we've traveled a total of 1 unit. The associated y values will go from f of 1, which is 2, to f of 2, which is 5, for a total amount traveled of 3 units. So if we've traveled a total of 3 units in terms of y, associated with 1 unit of travel in terms of x, then it's going to be 3 units of difference associated with that 1 unit travel, again in terms of x. So let's do one final example. So traveling from 1 to 1.5, so an even shorter distance. So now we need f of 1.5, because again our formula is going to be f of 1.5 minus f of 1 divided by 1.5 minus 1. So f of 1.5 is defined as 1.5 squared plus 1, and let's just verify that in the calculator. So 1.5 squared, and then we add 1 to that. That's going to give us 3.25. Okay, so our average rate of change based on that formula, 3.25 minus f of 1, which is 2, divided by 1.5 minus 1. So 3.25 minus 2 is going to be 1.25, and then 1.5 minus 1 is going to be 0.5. So now we're doing this division. So 1.25 divided by 0.5 comes out to 2.5. There we go. So that's going to be our average rate of change. So what I want you to notice here is as the x values grew closer to one another, notice that the rate of change also became smaller. That's because we're talking about function values at that point that are going to be closer together, closer to one another. So overall it makes sense that we would have an associated rate of change that's smaller because we're talking about traveling a smaller distance both in terms of our x and our function values, our y values. So we've looked at 2 different ways we could write this formula for average rate of change. So one of them uses y notation for our outputs. One uses function notation for our outputs, which is going to be preferable for us. There's also one additional way to represent the average rate of change, something that we call the difference quotient. And this is going to be what we use when we look a little bit further about this from the actual calculus standpoint. So as of right now, average rate of change is something that you talk about outside of calculus. We're going to take this one step further and we'll add in the calculus stuff, specifically what we've talked about with respect to limits. So the difference quotient is defined as follows. So the average rate of change of our function, f of x, with respect to x, which is another way of saying the rate of change of y with respect to x, is also called the difference quotient. And the difference quotient is this expression. It's defined as f of x plus h minus f of x divided by h. And even though this looks quite a bit different, we have different variables, the structure looks a little bit different from the other 2 formulas for average rate of change, it is logically equivalent. It means the same thing both from an algebraic standpoint and from the graphical standpoint, the geometric standpoint. So this represents the slope of the secant line that would pass through the points x and f of x, whatever x is, and a point where the x coordinate is defined as x plus h, and the y coordinate is defined as f of x plus h. So if those were the two ordered pairs that we passed our secant line through along our function's graph, then the slope, the average rate of change of that secant line, would be defined using the formula written above. So we can actually see this from the graph if we just label things a little bit differently. So same graph, same picture, but now we're going to label things slightly differently. And let me change colors so that it's clear we're looking at something slightly different. Okay, so before we thought of the two values as x1 and x2, two separately defined x values. Now let's think of them in a slightly different way. So rather than thinking of it as two distinctly defined x values, I'm going to call the first one just x. And then rather than thinking of this as a totally separate x value, I'm just going to think of it as a new x value that I reached by starting at x and traveling some distance to get to another x value. In other words, take the coordinate at x and add on some distance that we're going to call h. So if I travel from x a distance of h units, then the new x value I would end up at would be the value x plus h. So it would have this same coordinates value plus some distance, and that would take us to a further out x value, what we call x plus h. Well, based on this new labeling in terms of our x coordinates, we could also relabel our y coordinates as well. So this particular value would then be defined as f of x, since it's associated with the x value that we're just calling x. And this one would then be called f of x plus h, since that's the new labeling for that x value. So ultimately, it's the same picture, it's just a different way of labeling that picture. But assume we went with that particular version of the labeling, what would our average rate of change look like? In other words, if we were to take the corresponding values in this average rate of change formula and replace it with this new notation, what would happen? Well, f of x2 has now become f of x plus h, f of that further out x value. So f of x plus h, and then f of x1 is now called f of x. Okay, and then our denominator has changed as well. x2 we're now calling x plus h. In other words, our starting x plus a little bit of distance. And then x1 is now called x. So that means our denominator is now going to be x2, which we relabeled as x plus h, minus x1, which we're now calling x. Now, we cannot simplify anything in the numerator. Those would not be considered like terms. This does not mean multiplication. We can't distribute x. We can't just split up x over x and h, or split up f, over x and h. We just leave the numerator alone. However, we do have two like terms in the denominator. So notice we have a positive x, and then from that we're subtracting an x. So those like terms would actually be eliminated based on this new formula. And if we were to simplify down, what we're left with, again, same numerator, that hasn't changed, so f of x plus h minus f of x, but because of those like terms that reduce to 0 in our denominator, now all we're left with in that denominator is going to be h. And that is the difference quotient. So this particular expression right here, this is what we call the difference quotient. So again, it's just another way of writing average rate of change, just using a different labeling scheme. But this is going to be the version of average rate of change that we're then going to use and take one step further and look at in a little bit more detail. So we'll add in the calculus component to this later. For now, we just want to focus on using this difference quotient, determining what the difference quotient actually looks like for our specific functions that we're looking at. So So let's look at another example using the difference quotient this time. So for the function f of x is equal to x squared, we want to find the value of the difference quotient, the value of this average rate of change, using this new formula, under three conditions. So specifically, first, when x is 5, in other words, that's our starting x value, and then h is 1, which means we're starting at 5 and then traveling 1 unit away from 5. Think of h as a distance. I'm going to make a note of that. Think of that kind of like a distance traveled in order to get from our starting x value to then our next x value. So x is 5 and h is 1, and then x is 5 and h is 0.1. So again, we're traveling some distance away from that starting x value. But now rather than traveling a whole unit, we're traveling only a tenth of a unit away. And then finally, x is 5 and h is 0.01. In other words, just a little bit closer to where we were before. Okay, so let's evaluate the difference quotient under these different circumstances. So f of x plus h minus f of x divided by h. So here, when x is 5 and h is 1, that's going to be f of x, which is 5, plus h, which is 1, okay, minus f of x, which in this case is going to be f of 5, divided by our value h, which is 1. Okay, so that's really going to be f of 6 minus f of 5 divided by 1. So again, we need these two function values in order to evaluate this expression. I'm going to go out to the side, I'm going to find those. Now f of 5, we're going to need for all three of these, because notice we have the same associated starting x value for each three of these situations. So that particular value we will recycle. So our function is x squared, so that's going to be 5 squared, which is 25. And then f of x plus h, in this case f of 5 plus 1, or f of 6, is going to be 6 squared, which is 36. Okay, now make sure when you put them into the formula that you put them in the correct order. It's f of 6 minus f of 5. So f of 6 is going to be 36 minus f of 5, which is 25. We're dividing that by 1. 36 minus 25 is going to be 11, and anything over 1 is itself, so that's going to be 11. So this would be the average rate of change per unit in terms of change in y with respect to change in x. If we're talking about starting at an x value of 5, traveling 1 unit from there, and then comparing the associated function values, the associated y values. Now let's repeat, same x value, but now we're traveling a shorter distance away from this x value. So rather than traveling a full unit away to an x coordinate of 6, now we're only traveling a tenth of a unit away. So our difference quotient is f of x, which is 5, plus h, which is 0.1, minus f of x, which is still f of 5, divided by h, which is 0.1. Okay, so that's going to be f of 5.1 minus f of 5 divided by 0.1. Okay, so we need f of 5.1. So let's go to the side and calculate that. So f of 5.1 is going to be 5.1 quantity squared. Let's see, so 5.1, we square that, that's going to give us 26.01. Okay, so sub in 26.01. Now remember, f of 5, we already calculated that. That's going to be 25. So minus 25 divided by 0.1. So 26.01 minus 25, 1.01 divided by 0.1. And again, feel free to use your calculator. 1.01 divided by 0.1. That's going to be 10.1. So in this case, where we start at 5 and we travel a shorter distance, the rate of change per whole unit is going to be 10.1 to take us that far. And then let's go one step further. So again, starting at an x value of 5, but now traveling an even shorter distance, just 100th of a unit away, and then drawing a secant line, taking the slope of that secant line using this difference quotient. So that's going to be f of x plus h minus f of x, which is f of 5, divided by h, which is 0.01. Okay, so f of 5.01 minus f of 5 divided by 0.01. Okay, go to the side, calculate the new function value. F of 5.01 is defined as 5.01 squared which evaluates to 25.1001. Okay, so sub that into our difference quotient formula. So 25.1001 minus f of 5, which is 25, divided by 0.01. Okay, so 25.1001 minus 25, we'll essentially just think of the 25s as canceling. So 0.1001 divided by 0.01. So 0.1001 divided by 0.01 is 10.01. So again, notice what's happening to these rates of change as we decrease the distance between the two x values between which we're calculating the slope of that secant line. This is very similar to what we did with limits when we talked about evaluating a limit numerically. The idea is that we wanted to use specific x values that were a short distance away from an x value in question, the x value with respect that we're taking the limit with respect to. But the idea was we looked at x values that were close to it, increasingly close to it. So think of this as using an additional x value that's 1 unit away from our original x value, using an x value that's a shorter distance, maybe 1/10 of a way, and then using another one that's maybe an even shorter distance, 100th of a unit away. So what we're doing here is very similar to what we did with those numerical limits, the idea that we're getting closer and closer and closer to something. The smaller the distance gets, the closer we're getting to just 5 and then something that's infinitely close to 5. So there's something with a limit going on here, this idea of how the h values are changing. So what's really going on here? Well, that's something we'll look at in the next video. We'll formalize this idea of shrinking this distance, shrinking this value h, making it smaller and smaller, what that really means, and then what that means big picture, grand scheme from the calculus standpoint. So this is just one approach to calculating the difference quotient. So we actually calculated the value from scratch for each individual value of x and value of h. And so we basically had to do the whole calculation every time and find each of the function values from scratch every time. And keep in mind, we had the same x value each time, the same starting value. But if we had changed that value, say this had been 5 and this had been 6, we would have to do both output calculations in order to apply the formula to the new x value and the new h value. So rather than actually doing it by hand for specific values each time, typically it's going to be easier to use the difference quotient rather than using specific values of x and h each time. Use it to find a simplified form with no specific values. Take the difference quotient as just an expression. Let's see, I already have the word form there. So find a simplified form, or what we can think of as a formula for the difference quotient for just x and h in general. In other words, imagine taking this particular expression and evaluating what this expression would look like, not with specific x and h values, but just x and h in general, but what f of x plus h and f of x looks like for this specific function, f of x is equal to x squared. So if we just plug in the function as a whole and not the function evaluated with specific x values, then what we end up finding is a formula for the difference quotient, a simplified version of the difference quotient that we can use for any combination of values in x and h. And in most cases, that's going to be a major time saver, particularly if we want to use the difference quotient a few different times for a variety of different values. So let's see what that's going to look like. And that's what we're going to focus on for the rest of the video. Taking that difference quotient and then determining what the formula would be for the difference quotient with different function values, different function rules. So we want to find a simplified form of the difference quotient for that same function that we just looked at, f of x is equal to x squared. And then we want to essentially do what we did in the previous example, but use this formula and see how much less time it takes once we can use the formula rather than having to start from scratch and do all those individual calculations every time. So I'm going to start by writing down the actual expression for the difference quotient. So f of x plus h minus f of x divided by h. And then we are evaluating this particular expression if our function f of x is defined as x squared. So what does f of x plus h mean if we're talking about a function defined having a rule of x squared? Well, what it means is we're going to use the rule for f. We're going to apply all the steps that f says to apply, but we're going to apply them specifically to an input of x plus h. So in other words, in our function rule, wherever there's an x, a generic input of x, we're going to replace that generic input with the specific input x plus h. So f of x is x squared, which means f of x plus h is going to be x plus h quantity squared. So all I'm doing is I'm taking this particular function and I'm subbing in an input of x plus h rather than just the generic input of x. Now from this, and I'm going to put brackets around this so we show that this is its own thing, that is just f of x plus h. From that we are subtracting f of x, no changes, nothing special done to it. So we're subtracting just f of x, which is defined as just x squared. And then we're dividing all of that by h. Okay, now we need to simplify all of this down. What we want to focus on at the moment is simplifying the numerator, cleaning up that numerator, combining anything that combines. Now where we need to focus first is this first term where we have this binomial and we're squaring it. Be very careful when you see something like this. You cannot simplify this by just distributing the square to the two terms. That is not what this means. Remember, what squaring means is multiplying by itself. So technically what's happening here, what this is telling us to do, is to take x plus h and then multiply it by itself. So I'm going to go up here to the top and I'm going to do this separately. So rather than thinking of it as x plus h squared, let's think of that as x plus h times x plus h, which is what it really is. Okay. The acronym we can use to simplify this distribution is FOIL. So we multiply the first pair, the outer pair, the inner pair, and then the last pair together for a total of 4 multiplications. So if we multiply the first pair together, x times x is going to give us x squared. Okay, the outer pair is x times h, so plus x times h. The inner pair is h times x, so plus h times x. And then the last pair is h times h, which would be h squared. Okay, now x squared and h squared, different terms, they don't combine, but notice the two in the middle, xh and hx. Those are actually the same thing. Multiplication is what we call a commutative operation. So we can multiply x times h or h times x or x times h, and it's the same thing. So these two are technically like terms. So we have a single xh and then another, what we can think of as xh. So we have 2 of them in total, and we're going to combine those together. So that means we have x squared plus 2xh plus h squared. So that is going to be the simplified version of f of x plus h, and we can substitute that now into our difference quotient. So x squared plus 2xh plus h squared minus x squared. All of that divided by h. Don't forget the denominator. Okay, now as we simplify a variety of different difference quotients, the goal at the very end, if we've simplified everything correctly, is to be able to eliminate that h in the denominator. 99% of the time, we're going to be able to eliminate that h in the denominator. So what you're going to notice as we continue doing these problems is specific things at this point in the problem are going to cancel one another out. They're going to reduce to 0. Specifically, any term that does not have an h as part of it will end up reducing to 0. So at this moment, we're matching up like terms, but all of the like terms are going to match in a very specific way. So notice we have a positive x squared, and then over here we're subtracting an x squared. So those two terms are equal and opposite, which means they cancel out. Now these other two terms, not like terms, and there's nothing we can do with them. But again, notice what they have in common. There's an h in common in both of those terms. So let's write what we're left with. We're left with 2xh plus h squared, and then also that denominator of h. So as I mentioned a moment ago, the goal ultimately is to be able to get rid of that h in the denominator. What I now notice in the numerator is that these two terms have a factor of h in common. So in the first term we have an h, in the second term we have two h's. So the greatest common factor between the two terms in the numerator is going to be that common h. So I'm going to factor that out. Now from the first term I'm left with 2x, and then in the second term I had an h squared. If I factor out an h, I'm left with a single h remaining, and then that denominator of h. Once this h is factored out, I now have a common factor in the numerator and denominator, which cancels, reduces to 1. And all I'm left with is 2x plus h. And at that point, those two are not like terms. They can't combine. We can't do anything else with that. So we're done. So what we've now found is a simplified form of the difference quotient. In other words, if we think of the difference quotient as calculating the slope of a secant line, given an x value and then h, which represents how far we're traveling to get from that x value to another x value, this is now a simplified formula for the slope of that secant line. So rather than having to take all the time we took to evaluate the difference quotient in this way, using specific values of f and h and having to start from scratch every time, we now have a much simpler version of the difference quotient just based on how our function was structured, algebraically speaking. So if we want to evaluate the difference quotient for specific values of x and h, we could start from scratch using our function, or we can use the simplified version of our difference quotient, which is going to be a major time saver at this point. So using this new simplified formula, let's reevaluate all of those difference quotient values that we did in the previous example. So for the first part of the example, we had x was 5 and h was 1. So in that case, the difference quotient, 2x plus h, is going to be 2 times 5 plus 1. 2 times 5 is 10. 10 plus 1 is 11. And that was the same thing as what we got in the previous example. Now we also had x was 5, and then we traveled a shorter distance. Let's see, that should be a comma. And h was 0.1. Okay, so the value of our difference quotient, the slope of that secant line, is going to be, again, 2 times 5, but now we're adding on a smaller amount for h. We're adding on 0.1. So 2 times 5 is going to be 10, and then 10 plus 0.1 is going to be 10.1, which again, same value as what we got before. And then the final pair was x is equal to 5, and then h is equal to 0.01. So again, the idea was traveling a distance of 1 unit, then traveling a little bit shorter distance, and then a little shorter distance still, so that gradually we're approaching this value of 5 using a value that's further out than 5, but grows increasingly close to that original value of 5. So we have 2x plus h, so in this case, again, still 2 times 5, but now we're adding on a smaller h. So 2 times 5 is going to give us 10. So 10 plus 0.01 is 10.01, which again, same value as what we got before. So particularly if we're going to do this repetitively, it is helpful to have a formula for the difference quotient rather than just starting over every time and calculating it by hand using whatever values we're using. And we're also going to need this simplified formula in a different way once we start talking about instantaneous change rather than just average change. So again, average change means change over an interval, starting at one x value, going to another x value that's further away. What's the average change per unit as we travel across that interval on our function? Well, what we're later going to talk about is instantaneous change. So rather than looking at change over a range of x values, talking about the instantaneous change at a single point, a single x value. How is it changing at that single point in time if you were able to zoom way in on that single point? We're going to use this expression, this simplified version of the difference quotient, to look a little bit more closely at that concept of instantaneous change. But before we do that, let's just focus on calculating these difference quotients, getting this actual formula. Now, the more complicated the function is that we're looking at, the more complicated it becomes to find this simplified formula for the difference quotient. So we want to look at a couple different situations where using the algebra to simplify that difference quotient is going to be a little bit more complicated. It's going to require some different algebra skills. Okay, so our next function, g of x, is defined as 1 over x, and we want to find the simplified form of the difference quotient for this function. Now keep in mind, just like x and h are kind of arbitrary labels, f and g are kind of arbitrary labels as well. So when we talk about the difference quotient, we're talking about the specific structure of that expression. But if the function we have is called g, then that means when we write the difference quotient, it's just going to be a g instead of an f. But otherwise, it will be an expression with the same structure. So here, our difference quotient in general is g of x plus h minus g of x divided by h. Okay, and we don't know what x is, we don't know what h is. We want to find a formula for the difference quotient so that we could apply it to any value of x and any value of h. So our function is defined by the rule 1 over x. So g of x plus h means take that rule, and wherever we have the generic input x, we're going to put the input x plus h instead. So g over x plus h is going to be 1 over x plus h. Then from that, we're subtracting just g of x by itself. So just 1 over x. And then all of that is going to be divided by h. So we have fractions inside of fractions. We have a complex fraction here. Now, just like with the previous example, we want to start by focusing on the numerator. Simplify the numerator as much as we can. In this situation, that means finding a way to combine those two rational expressions. Now, they're subtracted, and then we know in order to add or subtract rational expressions or fractions, we need to have the same denominator. So at this moment, we need to get a common denominator. So these two denominators, each is a single factor. This one has two terms, but it's one factor. So this factor as a whole and this factor as a whole have nothing in common. So that means the common denominator that we need is going to require both an x plus h and an x. So our least common denominator is going to have the factor x and the factor x plus h. So that's what we want to convert these to. We want to convert them to equivalent forms that have this as a denominator. So for each of these fractions, we're going to need to multiply in the numerator and denominator by whatever it's going to take to get that matching denominator that we want. So this particular first rational expression, we've got the x plus h, but we're missing the x. So I'm going to take this one and I'm going to multiply top and bottom by that x that I'm missing, and I'll write this in an additional step. So 1 over x plus h, I need an x to get that common denominator. So I'm going to multiply in the numerator and denominator by x. Now the second one, we've got the x, but we're missing the x plus h. So similarly, I'm going to take that rational expression, multiply in the numerator and denominator by whatever it is that I'm missing. In this case, it's the x plus h. Don't forget the h in the denominator, that's still there. Okay? So let's see if we can do a couple things at one time. We're now going to have a common denominator in the numerator of x times x plus h. So that's now going to be the denominator in the numerator. What are our new numerators going to be? Well, 1 times x is going to be x, and then over here we're going to have subtracted x plus h. So let's go ahead and combine all of those, and let's put them over that one denominator. So for the first rational expression, I have my common denominator, and then I have an x as that numerator. And then in the second simplified rational expression, again, same denominator, and in the numerator we have 1 times x plus h, so just x plus h, but it's being subtracted, so we want to make sure we put parentheses around it when we simplify that. And again, don't forget the h in the denominator. Okay, so inside the numerator, nested, what happens here? Well, notice we have 2 matching terms that are just an x, so they reduce to 0. What does that leave us with? Now be very careful here. We have an h, but notice it was subtracted. That subtraction distributes to both terms in parentheses. So that means we now have a negative h on top. And you can just leave that denominator there undistributed. Just leave it as it is. So that's going to be x times x plus h. Now, before I write that division by h, that's still going to be fractions within fractions. Now, a fraction over another fraction, that also means division. So remember, this fraction bar also means division. We don't really have a procedure truly for dividing fractions. We have a way of converting division to multiplication in order to do fractional division. So dividing in terms of fractions, that's also defined as the same thing as multiplication by the reciprocal of whatever it is we were dividing by. So if we're taking our simplified fraction, this is the simplified fraction, dividing by the quantity h, that's also the same thing as multiplying by the reciprocal of h. Now h, you can think of that as h over 1, so if you take its reciprocal, that is going to be 1 over h. And that now at least gets rid of that complex fraction, but it does something else as well. What was the goal that we had for the last one? It's the same goal for all of these problems. The goal is to be able to eliminate that h in the denominator. So let's trace it. Here, 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 here. And then when we convert it to multiplication, this is now that particular h. But the benefit of once we convert to multiplication is, notice we now have something where we can cross out along the diagonal. We have common factors. So there's a common factor of h in this numerator and h in this denominator. So they divide out and reduce to 1. Now be careful with what we're left with. Now we just need to clean it up and we'll be done. What do we have in the numerator? Well, we still have a negative, which represents a negative 1. And then we have a 1 over here. So negative 1 times 1 is going to be negative 1 over our common denominator of x times x plus h. So that is going to be the simplified form of our difference quotient. And you could distribute that x in the denominator if you want, or you can just leave it alone based on what we're going to do with it later. That will be fine just to leave it alone. So that's a little bit different. Same goal, same kind of steps, but the algebra that it takes to simplify the difference quotient just looks a little bit different because our function looked a little bit different. Okay, let's look at one more special situation for one specific kind of function. So we looked at a polynomial function, we looked at a rational function, now let's look at a radical function, something that has a square root in it. So the strategy here will also be a little bit different. So we have h of x is equal to the square root of x, and we want to find the simplified form of the difference quotient. So in terms of the function h, the difference quotient is going to be h times, or h of, then it's going to have to be x plus h, which is not ideal. So let's call it something different for just a moment. Let's call it maybe x plus a, something like that, just so we don't get confused there. Minus h of x divided by, remember we're not calling it h anymore, we're going to call it a, just temporarily. And we can change back to another notation at the end if we want, or we can just leave it. Okay. So what is this going to look like? Now, same idea as before. H of x plus a in this case just means we're going to take the rule for the function h and then sub in this specific input. So that's going to be the square root of x plus a, and then we're subtracting h of x, so minus the square root of x, all divided by a. Now you have to be very careful here. It's very tempting to do something specific that you cannot do. You cannot actually combine those two radicals together. They're both square roots, but what's under each radical is different. We call that the radicand. Whatever's under the radical in this case is different. So these are not like terms, they do not combine. One thing that's tempting to try to do is maybe take this square root and split it up into square root of x plus the square root of a. There is no rule that lets you do that. You cannot split up a square root across addition. So these two are like terms. There's nothing you can do with those. So at that moment, there's also nothing you can do to get rid of this a. Here's where we have a different strategy that's specific to this type of function. So when we had a rational function, we ended up needing to get a least common denominator, and then we went from there. That was specific. It was a specific strategy to that kind of function. We have another strategy here that we call multiplication by the conjugate. So the conjugate, let's define what a conjugate is. The conjugate of something like a minus b, since we have subtraction here, would be a plus b. Or if you started with a plus b, then its conjugate would be a minus b. So the conjugate is going to be the binomial that has the same terms, but the opposite operation in the middle. If it starts as subtraction, it becomes an addition. If it starts as an addition, it becomes a subtraction. As it turns out, there's something specific we can do with radicals by using the conjugate. And this is going to look similar to what we did in finding a least common denominator. When we found the least common denominator, we converted our rational expressions to a form we wanted by multiplying on top and bottom by whatever was missing from that denominator. Here, we're going to multiply on top and bottom by the conjugate. In other words, specifically the conjugate of the numerator. So one term minus another term, its conjugate is going to be the same term plus the same term, plus that second term. So we're going to multiply in the numerator and in the denominator by the conjugate of this numerator. So on the top, multiplying by the conjugate again is going to have the same terms, so the same radicals, but rather than a subtraction, it's going to have an addition. And I'm going to put parentheses around it because this is not going to be as simple as just a plain old distribution. We now have multiple terms that have to get multiplied together. Now whatever I do in the numerator, I have to do the same thing in the denominator to keep everything in balance. So in the denominator, I'm also going to multiply by that conjugate expression. And this is going to be the strategy we use in pretty much any situation where we have a radical function and we want to find and simplify the difference quotient. Now the denominator, not much is going to happen there, and we're also going to leave the denominator undistributed just like we did before. Remember, the goal is to eventually be able to get rid of that original denominator. So by distributing, we put ourselves in a position where we may not be able to eliminate it as easily. So as before, we just want to focus on cleaning up that numerator. What can we do with the numerator? Well, let's put parentheses here. We now are foiling again, just like we did with that first example where we had that x plus h squared and we needed to clean that up. Same kind of thing here. And if you want, you might go out to the side and just do that multiplication outside of the context of the problem and then bring it back in. So I'm going to put a dot, dot, dot. We'll pick up in a little bit. I'm going to do this particular multiplication, these two numerators, just separately by themselves. So square root of x plus a minus the square root of x times, same terms, square root of x plus a, but now we're adding. Okay, so when we do this distribution, first outer, inner, last. So the first pair, square root of x plus a, and then we're also multiplying it by the square root of x plus a by itself. So I'm going to write that rather than truly two things multiplied together. If I'm multiplying something by itself, another way to write that is just that term, but squared. So that's going to be the first pair. Now the outer pair, square root of x plus a times the square root of x, okay, so plus the square root of x plus a times the square root of x. Okay, our inner pair, notice now we have a negative attached to this, so when we multiply a negative and a positive, the result is going to be a negative first and foremost. And then we have the square root of x times the square root of x plus a. Okay, and then the last pair, again, negative and positive, so it's going to be negative square root of x times square root of x. Anything times itself, again, we can write that with an exponent of 2. So minus the square root of x quantity squared. It looks like there's a lot going on here, but believe it or not, this is going to simplify down really, really nicely. First thing I want to look at is those squared terms. Okay, so we have a square root, and we're then squaring it in two different locations. Well, a square root and a square are defined as inverse operations. One cancels out the other, just like addition and subtraction cancel each other out. So in that case, this particular term and this particular term, the radical is eliminated by that matching exponent. So this is just going to be an x plus a, and this is just going to be an x, but of course it will be subtracted. Now before I write anything down though, let's look at the other two terms. We now have square root of x plus a and square root of x, square root of x and square root of x plus a. So just like with that first example where it was xh and hx, remember multiplication, the order we do it in doesn't matter. So these two terms both have the same factors, the same components, and one's added and one's subtracted. So just like before, they combine, but here they combine in a different way. Before, they both had the same sign, so they truly combined into one larger term. Here, they're the same, but they're equal and opposite, which means they're going to cancel out. They're going to reduce to 0. So a positive term, subtract the same term, they reduce to 0. So the square root goes away here, the square root goes away here, and these two terms are eliminated entirely. So that means we're left with an x plus a from that first term minus an x from that additional term. Well, what happens here though? We have an x minus an x, so those also go away, and we're just left with a. So believe it or not, all that multiplication in the numerator just comes out to a. So now, let's go back down here. Let's pick back up where we were. So our numerator, all of that simplifies just to a. Okay? And then our denominator, again, you don't need to distribute. It's just a multiplied by that factor. So a times the conjugate that we multiplied by, square root of x plus a plus the square root of x. Think back to what the goal was, what it's been for all of these. The goal is to get rid of that denominator if at all possible. Well, here it is, here it is. That's going to be that original denominator as before. But notice what happens now. Look at what we have in the numerator. We now have an a in the numerator matching that factor of a in the denominator. So again, they reduce to 1. What are we left with in the numerator though? Reducing is dividing. We're dividing something out. Division doesn't result in 0. Dividing something by itself results in a 1. So that means we have a 1 in the numerator. And then our denominator is going to be square root of x plus a plus square root of x. And so that's going to be fully simplified. And of course, if we want to have the h again, we can bring that back in now. So that would be 1 over the square root of x plus h plus the square root of x. That will be our difference quotient. So just to summarize what we've talked about in this video, we introduced this concept of average rate of change of a function over an interval. We can model it geometrically by drawing a secant line between the 2 points across that interval we're interested in, and then taking the slope of that secant line. Finding that slope represents that rate of change. In other words, how the y values are changing per unit of change in terms of the x values. And then we looked at the difference quotient, which is just another version of that average rate of change formula. We simplified the difference quotient, and so now we've seen a few examples of how that can look. That's going to be what we focus on, and that's what we're going to extend to this idea of calculus, how the calculus is going to be used. Specifically, we'll revisit limits, and we're going to combine the difference quotient with a specific limit, and that's going to define something very specific that we use in calculus.